Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we're continuing with integration, looking at the first of 3 videos where we will discover how integration might be applied. This video's applications relate to mean value, area and length. So if you're ready to learn, then let's get into it. So to start with the mean value, let's consider a function f of x over a specified interval a to b. So this is this f of x here between a and b. And the mean, or our average of f of x over this interval, will be this f bar. To put that into words, so the mean of f of x can be written as f bar always equals 1 over b minus a times by the integral from a to b of f of x dx. So it's saying f bar is the height of this rectangle whose area is the same as that of beneath the curve under the same range, or same domain. Influenced by quantum mechanics, this f bar has another notation which is shown by these triangular brackets, so f is the same as f bar. Another way of finding an average for a function is to use the root mean square value of f of x. So we might write f of root mean square, or to use the more modern notation, like this Dirac notation here, that would be of f squared square rooted, and this is equal to, as indicated by this notation, it's going to be 1 over b minus a times by the integral from a to b of f squared x dx, and all of that is square rooted. Both f bar and the root mean square value characterize the function over that interval. And if I just give you an example of the difference between the two values that you might get for a sine wave, we could say, well, f bar, so sine x with these Dirac brackets, is going to equal 1 over 2 pi times by 0 to 2 pi. So our a is 0 and our b is 2 pi, so b minus a is 2 pi. And then we have sine x dx. Well, this is just going to equal 0. At 2 pi, this will be minus cos x, this will be minus 1, and then at 0, it will also be minus 1. And so we'll just have minus 1 minus minus 1, which is 0. And that's the same for cos x, where we'd just have, instead we'd have a sine, and it would be sine of 2 pi is 0, and sine of 0 is 0, so that will also be 0. So this mean value is just 0. Whereas if we look at the root mean square value, so sine squared x, and this will be square rooted, would be 1 over 2 pi times by 0 to 2 pi of sine squared x dx. And you can use the double angle formula to work this out, as I showed you a similar case in the last video. And this will result in the square root of a half. That will be the result of that integral divided by 2 pi. And the square root of that is just 1 over square root of 2. So you can see our root mean square and our just mean value of the same function, sine x, over the same interval, does not give the same answer. It's 0 and 1 over root 2. Now let's consider areas in polar coordinates. So if we look at this left plot, we've got our function r of theta down here. We want to know the area on our interval theta 1 to theta 2. So that's our equivalent of x. So if it was f of x, we want to know the interval of theta 1 to theta 2, and that's got each their separate radii, r of theta 1 and r of theta 2. And so what we can do is take an infinitesimally small wedge section of this function, where we basically form a very thin triangle And the angle difference is just delta theta, a very small angle. And our area is what we're trying to work out, and we can then sum these up similarly to how normal integrals work in Cartesian coordinates. And this length here is r delta theta. It's just the radius times by the angle across. Therefore, the area, delta A, is approximately equal, because of it being a thin triangle, is approximately equal to a half the base, which is our r delta theta, times by the height r of this triangle, which is equal to a half r squared delta theta. And so when we put that into an integral form, it leads to our a equaling the integral from theta 1 to theta 2 of a half r squared d theta. And we're going to be summing up over this whole range to find our area. So a first example we could look at is a semicircle. So that has a known area as quite obviously just a half pi r squared. If we use the equation x squared plus y squared equals a squared, so here our radius equals a, and so the area will be a half pi a squared. That's what we should expect. I'll go through both Cartesian coordinates and polar coordinates to show they give the same answer. Starting with Cartesian coordinates, what we can see, we're integrating over this whole area from minus a to a, so our bounds, our limits are going to be minus a to a, and the area will equal that integral of y dx. And if you think about what we're saying is, as this is a symmetric function, this area is the same as this area, we can just say the whole area is 2 times the area from 0 to a. So for this next section we can write this is 0 to a times 2, and we're going to find y by rearranging this equation, our Cartesian description of a semicircle. So y is equal to the square root of a squared minus x squared dx. And our next step will be to substitute in saying let x equal a sine theta, and that means our dx will equal a cos theta d theta. And so when we substitute that in, we have 2 times the integral, and I'll do the limits in a second, of a cos theta d theta at the end instead of our dx. When we substitute in a sine theta here, we'll have a squared minus a squared sine squared theta. If we take a factor of a squared out, remembering to square root it, we're left with a times by 1 minus sine squared theta to the half, which is just a times cos squared theta to the half, so just cos theta. And so what we're left with is a cos theta times our a cos theta d theta. And our limits, when x is 0, theta must be 0 to make this equation work. So 0 is our lower limit. And our upper limit, for x to equal a, we must have sine theta equaling 1. So we're going from 0 to pi over 2. So that's the same as 2 times the integral from 0 to pi over 2 of a squared cos squared theta d theta. And again, if we use the double angle formula, this just results in pi a squared times a half. And I'll let you do that to show that. And this is obvious, as I was saying before, that's just the area of a semicircle. It's what we should expect. Now for polar coordinates, our equation is just going to be saying that r is a for the whole range of 0 to pi for our theta. So our area, a, equals the integral from 0 to pi of a half r squared d theta. Remember, that's our equation here. And our ranges theta 1 to theta 2 are 0 to pi. And so we've just got a half a squared, because our r squared equals a squared for that whole range, of 0 to pi of d theta. And that, again, is quite obviously just a half pi a squared, as expected, again, for a semicircle. So you can see whatever coordinate system we use will result in the same area, and it's the expected area of a semicircle. Now let's look at path length. So in our Cartesian coordinates, we can imagine this function, which follows this black line here, is of a length L, and we're trying to find what that length is. If we imagine 2 points, P and Q, and between them we write that delta x and delta y, and we draw a triangle to follow that, you can see in this visualization this bigger triangle, and the actual path that the function takes is this delta s. As we make this triangle smaller and smaller to fit closer and closer to the curve, where delta x and delta y are getting infinitesimally small, delta s is going to approximately equal the length PQ. So delta s will approximately equal PQ, which equals the square root of delta x squared plus delta y squared. And so what we can say from this is that delta s approximately equals, and if we take a factor of delta x out of this square root, we'd have delta x times by the square root of 1 plus delta y over delta x squared. Now, what we can use is this delta x as our variable that we're integrating over, and so we'd get our entire length is equal to the integral from a to b of ds, and now we can use this delta x, delta s substitution to see that this is equal to the area from a to b of the square root of 1 plus dy by dx squared, all square rooted over dx. So now imagine the same case, but instead we've got a parametric function where x is a function of t and y is also a function of t. So what we can do is the same as before, is find our delta s, and instead of writing delta s with this square root, I'll write delta s squared equals delta x squared plus delta y squared, approximately equals. And you can see that's just by squaring this across. And so from here we can say, let's take a factor of delta t squared out of delta x and delta y, as they're both functions of t, and we'd have that delta s squared is approximately equal to delta t squared times by delta x divided by delta t all squared plus delta y divided by delta t all squared. And from here we can now take the square root, and you'd see that our integral will therefore become L equals the integral from this t at a, whatever t value gives our x equals a or y equals a point, and same for b, times by dx by dt, and if t was time, we'd have x dot squared plus y dot squared. But if this wasn't time, you would just be writing in here dx by dt, and similarly dy by dt, all square rooted over dt. And that would be our parametric version for finding this length. Now, how might we work this out in polar coordinates? Well, if we start with just looking at another function here, and defining 2 points, Q and P, on there, we could say, if this is radius r, and this is a very small angle, this radius here is r plus delta r, or it would be r of theta plus delta theta, and therefore this difference here is r delta r, and this length here is just r delta theta. And so what we have is this triangle here represents this small triangle. So we've got our length across here, which is this one, as r delta theta, this is delta r, and then the actual curve that this function follows is this line here, our ds. And similar to before, we can draw a straight line between them and say, as delta r and delta theta get very, very small, this delta s is going to approximate to PQ, and so we can say that delta s approximately equals, or delta s squared approximately equals r squared delta theta squared plus delta r squared. And so if we now take a factor of delta theta out, we could say that delta s squared approximately equals delta theta squared times by r squared plus delta r divided by delta theta squared. And if we take a similar approach to before, our total path length L is going to be from A to B of ds. That's going to be the integral from A to B of the square root of r squared plus dr by d theta squared, all square rooted d theta. So to cement this idea between Cartesian and polar coordinates giving the same integrals, we'll do the arc length of a quarter circle. And so you should know this is just going to be a quarter of the circumference, so 2 pi a, and so we're just going to have a half pi a as the arc length of our quarter circle. So for Cartesian coordinates, we have x squared plus y squared equaling a squared, therefore y is the square root of a squared minus x squared. And just looking at what we had before for our ds, we're going to need to know what dy by dx is. So dy by dx is equal to minus x over a squared minus x squared square rooted. And from here we can use our path integral L equaling 0 to a, as we're just going from x equals 0 up to a, of 1 plus our dy by dx all squared, which is going to be x squared over a squared minus x squared, all square rooted, times dx. And so that integral will become from 0 to a of, if we combine this 1 and that fraction, we'll just be left with a squared over a squared minus x squared. And so if we square root that, we're left with a over a squared minus x squared square rooted. And that equals, and before we substitute in our limits, we'd be left with a arc sine of x over a. And that is going to be again from 0 to a, and this will just give us pi a over 2, as we expected, half pi a. Now if we do it in polar coordinates, all we're saying is that r equals a from theta equaling 0 up to pi over 2. And so again we might want to know what is our dr by d theta. Well, r doesn't depend on theta, it's always a. So dr by d theta equals 0. So we have L equaling the integral from 0 to pi over 2 of our r squared. If we look back at our equation, it's r squared plus dr by d theta squared. So this is 0, and our r squared is just a squared, and it's all square rooted, so it would be a squared square rooted, and we're left with just a times d theta. And obviously as a doesn't depend on theta, we can take it out of the integral, so it's just from 0 to pi over 2 of d theta, and so we're left with a half pi a again. So as you can see, no matter what coordinate system we use, we're left with the same path integral, the same areas. It doesn't really matter what coordinate system we use, just whichever you find easiest in that case. As a final example, if we consider this interesting case of the arc length for an infinite spiral, it's given by this equation in polar coordinates, and r of 0 is just 1, so we'll be starting here. So when theta is 0, e to the 0 is 1. Then when theta is 2 pi, we're left with e to the minus 1, so some smaller number in here. And so after one revolution, we'll be here, and it will keep spiraling in and in like that. What is the arc length of that spiral? So we know that theta is going from 0 up to infinity, so we're going to have an infinite integral here. And dr by d theta is just equal to minus 1 over 2 pi e to the minus theta over 2 pi. So for our path length integral, we'll have L equaling 0 to infinity of r squared, which is just e to the minus theta over 2 pi squared. So that will be e to the minus theta over pi, plus dr by d theta squared, which is just going to be 1 over 4 pi squared e to the minus theta over pi, all square rooted d theta. And if we take a factor of e to the minus theta over pi out, we'll be left with the integral from 0 to infinity of e to the minus theta over 2 pi, as we've square rooted it as we come out of that bracket, times pi, 1 plus 1 over 4 pi squared, all square rooted, d theta. This 1 plus 1 over 4 pi squared, all square rooted, has no dependence on theta, so we can take it out as a constant, and we'll be left with 1 plus 1 over 4 pi squared, square rooted, times the integral from 0 to infinity of e to the minus theta over 2 pi, d theta. Now if we do the integral, we'll be left with 1 plus 1 over 4 pi squared, square rooted, times minus 2 pi e to the minus theta over 2 pi for the limits 0 to infinity. If we substitute in those values, we're just left with 1 plus 4 pi squared, square rooted. So this infinite spiral has a finite length, which is quite an astounding result. Today we looked at how integration applies to mean value, area and length. In the next video, which is the second of the 3 videos of applications of integration, we'll be looking at how integration relates to centre of mass. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.